Dear students, in the last class, we have studied about the rules governing the electronic configuration like Afba principle, Pauli's exclusion principle, Hund's rule, N plus L rule, and extra stability rule. Today, we study about the anomalous electronic configuration, exchange energy, and also the electronic IUPAC nomenclature of the elements greater than 100. Although electronic configurations based on AFBA order of filling agrees mostly with those derived experimentally, yet there are quite a few exceptions due to one or two misplaced electrons. And these anomalies are given below. AFBA principle does not tell us which electrons are to be removed when an ion is formed from an atom. Example, in case of the air, the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d6. It has been experimentally confirmed by spectral and magnetic studies that Fe2 plus has configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d6 and not 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. This means that ionization results in the loss of 4s electrons in preference to 3d electrons, even though the 3d were the last to be added in building up the configuration of iron atom. It means in Fe2 plus 3d has lower energy than 4s, which is contrary to AFBA principle. From this anomalous, it is concluded that in the process of ionization, the first electrons are lost from the subshell with the higher n, and if n is the same, then from subshell with the highest L value. The second point, although n-1 d subshell and ns subshell lie quite close together, yet the formation is same watt higher in energy. Accordingly, the predicted AFBA outer configuration of chromium is 3d4 4s2, but experimental supported configuration is 3d5 4s1. Similar situation is found in case of copper. So actual electronic configuration of copper should be 3d9 4s2, but experimental result shows that it is 3d10 4s1. The reason for these deviations is extra stability rule associated with half filled and completely filled subshells. In the sixth period, the 4f and 5d subshells are exceedingly close in energy. In lanthanum 57, the last electron does not go to 4f, but it is added to 5d subshell to give configuration 4d10, 5s2, 5p6, 5d1, 6s2. However, the next electron for cerium, atomic number 58, is added to the 4f subshell instead of 5d. Here the previous electron, that 5d, is also shifted to 4f to give the configuration of cerium as the 4f2, 5d0, 6s2. The next one, the AFBA order configuration of zirconium is 5s2, 4d2, and that of the next element niobium would be 5s2, 4d3. But the experimental electronic configuration of niobium is 5s1, 4d4 due to higher stability associated with half-filled configuration. In case of technetium, where the atomic number is 43, the experimental configuration should be 5s2, 4d5, but the observed configuration is 5s1, 4d6. This shows that the preference for half-filled or completely filled configurations is not the only controlling factor, but some complex nuclear electron and electron-electron forces also have some role to play in determination of these configurations. Here I have shown some of the unusual electronic configurations of the different elements. Like chromium, so its electronic configuration should be actually according to the Aufbau principle, it is to be 3d4 4s2, but experimentally it is found 3d5 4s1. Similarly for copper, it should be 3d9 4s2, but experimentally it's found 3d10 4s1. Similarly for molybdenum, it should be 4d4 5s2, but experimental shows 4d5 5s1. For ruthenium, it is 4d6 5s2, but it is having 4d7 5s1. For palladium, the expected should be 4d8 5s2, but observed is 4d10 5s0. Similarly, these things are also given in this slide. So showing the copper has the electronic configuration, the 3d10 4s1, the silver is having the electronic configuration 4d10 5s1, and gold has the electronic configuration 5d10 4f14 6s1. And now the other elements are also given in the below slide. So this is a table. It shows the elements with green color. They don't violate from the electronic configuration as per the Aufbau principle. But the elements which are shown by the yellow, they deviate from the expected electronic configuration from Aufbau principle. So as we have already discussed about the chromium, then the copper also, for niobium, the expected is the 4d, the expected is the 4d 4 5s1. For molybdenum, it is 4d5 5s1. For ruthenium, it is 4d7 5s1. For rhodium, 4d8 5s1. For palladium, it is 4d10. For silver, 4d10 5s1. For lanthanum, as it is said, the 4f electrons are not filled. Its outer electronic configuration is xenon 5d1 6s2. For cerium, it will be 4f1 5d1 and 6s2. For gadolinium, it is the 4f7 5d1 6s2. And for the next, the platinum, it will be 4f14 5d0 6s1. Then for gold, it is 4f14 5d0 6s1. Now for actinium, so when we go for the actinium, so it is 6d1 7s2. For thorium also, it is 6d2 7s2. For protoactinium, it is 5F2, 6D1 and 7S2. For uranium, 5F3, 6D1, 7S2. For neptunium, it is 5F4, 6D1, 7S2. For curium, it is 5F7, 6D1, 7S2. And for lawrencium, it is 5F14, 7S2, 7P1. So these are all some of the electronic configurations of the anomalous electronic configurations. In case of palladium, the predicted AFBA configuration is 5F, 5S2, 4D8, but the experimental observation is 5S0, 4D10. This is the only case where the observed configuration has two misplaced electrons. Coming to the another aspect, that is exchange energy. This is nothing but the spatial stability associated with half-filled and completely filled subshells. According to Hund's rule, electrons distribute themselves in degenerate orbitals so as to keep like spins as far apart as possible. Electronic configuration of carbon is 1s2, 2s2, 2px1, 2py1, 2pz1. Of course, for carbon it is 2pz0, and for nitrogen it is 2px1, 2py1 and 2pz1. Now, this happens because in case of nitrogen, electrons as charged particle repel one another, and electron-electron repulsion is minimum when electrons with like spins in a subshell keep as far apart as possible. The stabilizing effect arises whenever two or more electrons with the same spin are present in the degenerate orbitals of a subshell. These electrons tend to exchange their positions, and the energy released due to this exchange is called exchange energy. Exchange energy is the energy released when two or more electrons with the same spin exchange their positions in the degenerate orbitals of a subshell. In other words, exchange energy is the energy released when the anti-parallel electrons belonging to a degenerate subshell are made to have parallel spins. The number of exchanges that can take place is maximum when the subshell is either half filled or completely filled. As a result, the exchange energy is maximum, and so is the stability. The exchange energy is the basis of Hund's rule. That is, electrons which enter orbitals equal energy have parallel spins as far as possible. The extra stability of half-filled and completely filled subshell is due to relative small shielding, smaller Coulombic repulsion energy, and large exchange energy. This slide shows about the exchange energy. The stabilizing effect arises whenever two or more electrons with the same spin are present in the degenerate orbitals of a subshell. These electrons tend to exchange their positions, and the energy released due to this exchange is called exchange energy. The number of exchanges that can take place is maximum when the subshell is either half filled or completely filled. As a result, the exchange energy is maximum, and so is the stability. You may note that the exchange energy is at the basis of Hund's rule, that electrons which enter orbitals of equal energy have parallel spins as far as possible. In other words, the extra stability of half-filled and completely filled subshell is due to relative small shielding, smaller or Coulombic repulsion energy, and large exchange energy. In this slide, it shows the first, that is, if the d orbital is associated with one electron, it is having the exchanges of 4. It can go to that electron can shift into the second, third, fourth and fifth. So therefore, the d orbital having one electron is having 4 exchanges. Similarly, the d orbital having 2 electrons will be having 3 exchanges. The d orbital having 3 electrons will be having 2 exchanges, and the d orbital having 4 electrons will be having only 1 exchange. If you add all these exchanges, it becomes 4 plus 3 plus 2 plus 1. It is equal to 10 exchanges. Suppose if the orbital is incomplete, that is, the orbital is having only 4 electrons. In such cases, the one electron 3 exchanges, second electron will be 2 exchanges, third electron will be 1 exchange, and there is no exchange for the fourth electron. Therefore, the total exchanges will be 3 plus 2 plus 1, that is equal to 6. So, in these two cases, the number of exchanges will be more in case of half-filled rather than the incomplete d orbitals. Therefore, the stability of half-filled orbitals is more. The similar information is given below also. Another reason for stability of half-filled and completely filled subshells is symmetrical distribution of electrons. It is well known that symmetry leads to stability. The half-filled and completely filled subshells have symmetrical distribution of electrons in them and are therefore more stable. Electrons in the same subshells, that is, here it is 3D, have equal energy but different spatial distribution. Consequently, their shielding of one another is relatively small, and the electrons are more strongly attracted by the nucleus. Here I have shown the electronic configurations and the arrangement of electrons in noble gases. So the helium, neon, argon, krypton, xenon and radon, these are known as the noble gases. Helium contains 2 electrons. The neon contains 8 electrons. The distribution of the 8 electrons is 2 and 8. The first shell contains 2, second shell contains 8 electrons. Similarly, argon is having the 3 shells. The first shell contains 2 electrons, second shell 8 electrons, the third shell also contains 8 electrons. Krypton is having the electronic configuration 2, 8, 18 and 8. Xenon is having the electronic configuration 2, 8, 18, 18 and 8. And lastly, the radon is having the electronic configuration 2, 8, 18, 32, 18 and 8 electrons. So this is a slide that shows the arrangement of the electrons in the atom. So from atomic number 1 to atomic number 20. That is the distribution of electrons in the K shell, L shell, M shell and N shell in various elements from hydrogen, helium, lithium, beryllium, boron, and so on up to the calcium. So this is a slide that shows the electronic configuration of the elements from atomic number 1 to atomic number 30. Students, go through these atomic numbers from 1 to 30 at least. So you must know the element name and its atomic number. And here I have shown the same, the outer electronic configurations. The hydrogen 1s1, helium is having 1s2, lithium is having the helium configuration with 2s1, beryllium 2s2, boron helium configuration with 2s2, 2p1, 2 up to neon, it will be the helium configuration with 2s2, 2p6. Similarly, for sodium, it is the helium configuration with 3s1, magnesium it is 3s2, aluminium it is 3s2, 3p1, 2. The next, if you go to the argon, it will be neon configuration with 3s2, 3p6. Next starts the potassium with electronic configuration of the outermost argon with 4s1, calcium argon with 4s2, and when we start from atomic number 21, they are all called the D block elements, which starts from scandium to the zinc. The scandium electronic configuration is argon with 3d1 4s2, the next titanium argon with 3d2 4s2, vanadium argon with 3d3 4s2. When we come into the chromium, it is not 3d4 4s2, it is 3d5 4s1. Similarly, for manganese, argon configuration with 3d5 4s2, iron with 3d6 4s2, cobalt 3d7 4s2, then the nickel with 3d8 4s2, the copper once again it is 3d10 4s1, but it is not 3d9 4s2. For zinc, it is 3d10 4s2. It is because of extra stability rule. So this is a table. It shows the electronic configuration of various elements. So up to 106. So this is also the electronic configuration of various elements. Now coming to the IUPAC nomenclature of elements with atomic number greater than 100. In the periodic table, the elements were normally named by the discoverers, and these names were accepted as such by IUPAC. However, the problems were faced in case of elements with atomic number more than 100, as different persons laid claims on the discovery of some of these elements. Example, element with atomic number 104. The Americans named it as Rutherfordium, but Russians named it as Kurchatovium. To avoid this, in 1994, IUPAC recommended the following method of naming the elements. In this method, the element is named with its atomic number using the numerical roots. The roots are to be put together in order of digits of the atomic number, and the suffix IUM is to be added at the end. The root words for digits are: for 0 it is given as nil, for 1 we write un, for 2 it is bi, 3 tri, for 4 quad, for 5 it is pent, 6 hex, 7 sept, 8 oct, and 9 n. These are the root words that they are going to use. Now, if an atomic number is 101, the element with atomic number 101, so it is named as IUPAC nomenclature of this number is For 1 it is known as un. For 0 it is nil. Next for once again 1 it is un. Last ium. So hence it is named as un, nil, un, ium. For 102 un, nil, by, ium. Instead of, because there are two I, one I becomes removed. Hence it is un, nil, bium. Similarly 103 un, nil, trium. 104 un, nil, quadium. Un, nil, pentium. Un, nil, hexium. Un, nil, septium. Un, nil, octium. Un, nil, ennium. And for 110 it is un, nil, 110 un, nil, ium. Un, nil, nillium. For 111 it is written as un, ium. For 112 un, bium. Un, trium. Un, codium, and so on. So this is how the names were given for the various elements by IUPAC. The same thing is given in this slide also, how IUPAC nomenclature is given. Of course, for some of the elements, the IUPAC also officially given the names of the research scientist. For 101 element, it is given as Mendelevium. For 102, Nobelium. 103, Laurentium. 104, Rutherfordium. 105, Dubnium. 106, Sibergium. 107, Bohrium, on the honorary of the Niels Bohr. So like this, so different scientist name up to 111 they have given in spite of the naming as IUPAC nomenclature. Students, go through these aspects and try to remember. Thank you.